Right, in the previous section, we talked about the CAPSET problem. And the proof of CAPSET problem was posted only on the on May 15, right? So Ellenberg posted a PDF file containing the proof of this problem. And there was lots of development quickly. So that was only May 15, and Giswick also wrote in the comments that he has the same proof, so they later wrote a joint paper. Now, on only in May 18, Terence Tao, who is a Fields medalist and who's a professor at UCLA, posted an article on the blog titled "A Symmetric Formulation of Their CAPSET Bound." I can share the screen. Right, this was May 18, 2016. And what Terence Tao was curious about is that the proof by Ellenberg and Giswick is not symmetric. You have A, B, C, right? So you have three. So you want to forbid the three-term arithmetic progressions. And the proof looks as if you treat the middle one differently from two others. Right? So how can you make a symmetric formulation where all three play the same role, right? Instead of only two making something, right? And then he came up with the idea called now it's called the slice rank. And after then, many papers cite this blog page to use slice rank because he didn't write it on a paper. Right? This is only on his blog. So today, in this video, I'm going to explain the material of this blog. Okay. Right, so I strongly suggest you to read this blog. Oops. Yeah, let's go back. All right, so let's start a function. Oops. So function f is called a slice if f can be written as a product of two functions where the one function only depends on one coordinate and the other function depends on the all other coordinates. Okay. Now we define slice rank. So for a function a to the k from a to the k to f, the slice rank of f is the minimum integer m such that f is a linear combination of m slices. All right, so we want to write an arbitrary function from a to the k to f as a linear combination of slices, where slices are the function that can be written as a product of two functions. One is from a to f, and the other is like you can split one coordinate from the others. So why is this called the rank? So if k is 2, then the slice rank of a function f a squared to f is equal to the rank of a matrix Aij. Okay, so let me say Fij, where I is in A and J is in A. Why? The reason is simple. There's a well-known fact, right? So remember from the introduction, from the course on Introduction to Linear Algebra, there is a theorem saying that every rank R matrix can be written as a linear combination of R rank 1 matrices. And any rank 1 matrix can be written as a slice. So, right, if you have a rank 1 matrix, right, there's a row that is up in the basis, then everything else is spanned, right? So you can make a rank 1, you can represent rank 1 matrix as a product of these two, right? You can think of this as a function depending on only one coordinate. Am I doing all right? Yeah, function depending on only one coordinate. All right, so maybe it's better to write it as the other formulation, right? So, I mean, I want to write it as a slice. Yeah, so if my matrix, my function f of x, oops. Right, it was correct. Yep. So any rank 1 matrix can be written as a product of two. Any rank 1 matrix you can simply describe by a product of two functions, right? Right. So the row is just represented by one vector here, column represent one number here, and product of these two become the entry, right? So it's a slice. So in the 2x2 matrices, rank is equal to the minimum number R, such that you can write your matrix as a sum of R rank 1 matrices, and rank 1 matrices are precisely the slice. If you think of the matrix as a function, of course, when I'm assuming that A is finite. Just for simplicity. All right. So you can think of this as a kind of generalization of a matrix rank to something called the hypermatrices. Where hypermatrices, in the matrix you only have a row and column, so only two components, right? So when you decide row and column index, then you determine the number. Now, in the hypermatrices, you have many coordinates, right? So in this case, you have k values to determine k indices, and if you decide k indices, you have a value. So function from a to the k to f can be seen as a hypermatrices. But anyway, we don't really care about this name. Here's an important lemma. So let k. So this lemma is on according to Terence Tao, he put it like this. It's the rank of diagonal hyper matrices. So let k is 2 and A be a finite set, and f is a field, and let f be a function from a to the k to f. such that f of x1, x2, xk is non-zero implies that it's all the indices are same. So that's why it's called diagonal, right? In the diagonal matrix, off-diagonal entries are zero. Now we are in the situation of hypermatrices. So whenever its indices are distinct for any pair, then it's zero. So in the case of the rank function, when you have a diagonal matrix, rank is equal to the number of non-zero diagonal entries. And here is the same. Then the slice rank of F is equal to the number of non-zero diagonal entries. And this is obviously true because, obviously true when K is 2, right? In the 2 by 2 matrices, slice rank is equal to the rank, and rank of the diagonal matrices is equal to the number of non-zero entries on the diagonal. So how do we prove this? We prove by induction. Induction on K. And if K is 2, it's trivial. It's 2 by 2 matrices. No, not 2 by 2. It's matrices, diagonal matrices. So we can assume K is bigger than 2. Now, furthermore, we may also assume f of A is non-zero for all A in A. Because otherwise we can restrict A. Take a subset of A, which gives a non-zero value. If this lemma is true for such a subset, then it's true for A. Alright, so we can delete such a thing. Alright, so for each A in A, let f of A x1, x2, xk be 1 if all these things are equal to k and 0 otherwise. So I'm defining function. Then is this a slice? Yes. It is a slice, right? So you must take a product of two functions, right? One function depends only on x1. If x1 is a, then it's 1 and 0 otherwise. And that's one function, that's h. And g is a function depending on x2 to xk. And if it's 1 if all of them are equal to a and 0 otherwise. And you take a product of these two, and that's the function f of a. So clearly this is a slice. And furthermore, f is a linear combination of f of a, right? Because, oh, it's a linear combination. Okay, so how do I write? Yes, f of a, and fa. Right? This is constant, right? We are given a function f, and that's constant number, and so for any x, this function is a linear combination of all these things, because for all off-diagonal entries you get 0. So it's the sum of these elementary hypermatrices. So therefore, this means that the slice rank of f is at most the size of A, right? Because I can write it as a linear combination of this many slices. Now we need the lower bound. So suppose that slice rank of f is at most A minus 1. Okay, now what does that mean? That means I can write it as a linear combination of slices, and some of the slices, okay, so let's see. Yeah, so let's do it this way. So we have alpha in II, so Fi alpha, so these are slices. Right, so this is Xi and X1, X2, Xi minus 1, Xi plus 1, Xk. So what this means is for some sets I1, I2, so these i's are the indices of the functions, right? So we have these two functions, and functions Fi alpha from A to F and Gi alpha from A to the K minus 1 to F, and alpha is in II, right? And I is from 1 up to K. And moreover, some of these indices, that's the number of functions. And the number of function is less than or equal to A minus 1. Because slice rank is at most A minus 1, so I can write it as a linear combination of at most A minus 1 slices. And each slice, well, depending on the variables which is split, it may take x1 out, or it may take x2 out. So depending on that, we have a variable I here. Now, we define W with the vector space of functions H from A to F that are orthogonal to all F K alpha for all alpha in IK. What I mean, in the sense that, so by orthogonality, I use some inner product. What is the inner product? The inner product is actually this one. For all A in A, if I take some of these product, no, not alpha, it's 0. Right, what does that mean? So you can think of this, right? So for two functions, let's not use f and g. For two functions h1, h2 from A to F, define the inner product as the sum of the h1a, h2a, right? And this is inner product because it satisfies all the actions, right? So when you have a linear combination of functions, then you can linearly expand it and a few other things, right? Yeah, you can swap and get the same value, and if it's 0, that means oh no, am I doing right? Yeah. And if this inner product is 0, then we call it orthogonal, right? Now, let D be the dimension. So what is the dimension of W? What is the dimension of W? Well, it's orthogonal to all these things, so it's actually dimension of the whole function space, that is okay, let me vector space of all functions h from A to F minus dimension of vector space of spans of these HIs, right? Oh, I had alpha. Okay, so fk alpha spans of all fk alpha, right? Because remember, W is the orthogonal complement of that. And what is the dimension of vector space of spans of all fk alpha? Well, the number of these functions is at most a minus 1. Oh, no. What I mean, it's ik, right? So dimension is at most ik. The reason why we have inequality is because some of them could be equal, right? Or some of them, they could be linearly dependent, so the dimension could be smaller than that. All right. So dimension of W is at least a minus I of k. Now, what I'm going to do is choose a function W such that its support, so which is the set of values where choose a function h in W such that the h of x is non-zero. So the set A prime is maximal. All right, how do I? Yeah, I mean, and then size of A prime is at least D. Why? Because if not, right, if size of A prime is smaller than D, then think of the linear transformation. From W to F to the A prime, right, where function F is mapped to F of this way, right? So this is linear transformation, obviously. And what happens is that dimension of this space is size of A prime. So the dimension of kernel of this map is equal to dimension of W, which is D, minus A prime. right? So if A prime is strictly smaller than D, then this is positive. So this kernel has positive dimension. So that means there exists a function such that when you send it by this linear transformation, it gives all 0 values. So there is a function h prime in W such that h of A is 0 for all A in A prime. Then consider h plus h prime. This is my new function. Then h double prime A is non-zero for all A in A prime. Oh, by the way, h prime is non-zero function. And the support is larger. Is non-zero for some B, not in A prime. Right? So the contradiction to the maximality. Of course, there are other arguments, but this is one argument saying that there is a function who has non-zero values for at least d many points. So let's take such a function as h. So h is a function in W so that h of A is non-zero for all A in A prime, and A prime has size at least D. Now consider the following sum for all in xk in A. We're gonna sum f1 xk and h of xk. Right? Now we apply these definitions. So what we end up is from 1 up to k and alpha in II and fi alpha xi and gi alpha. I'm copying it from the left hand side. And hxk. Alright? Now, let us rearrange terms. Okay? How do we rearrange? So let f prime x1, x2, xk minus 1. Oh, no, I'm not rearranging much. But the thing is, if I is equal to k, what's going to happen? So let's first leave the terms that I is not k. So these are the... Alright, let me just copy and paste. And what happens if I is k? Right. Oh, and also I forgot this. I forgot something too. What did I forget? we need the sum over xk. Right? Yes, we are summing over xk, and we have this thing. And what happens if oh now that's why I realize what's happening. So this is up to k minus 1, and what happens if I is equal to k? If I is equal to k, then alpha is in ik, and we are summing over all xk in a, and fi fk alpha xk and gk alpha x1 up to xk minus 1 and hxk. Now this times that, the sum of these two, right? So let me do it again. Oops. Okay, let me do it again. What's happening? So let me first copy the first one. So fi alpha xi, and sum of these. In this case, this is 1, and then alpha in ik and sum of xk. No, in this case, let's take this part out because this doesn't have xk. So I'm collecting terms gk alpha x1 up to xk minus 1 and sum of xk f of k alpha xk and h of xk. But this term is 0 because h is in w. Right? So this is what's gonna happen. So what end up is only these terms. All right, now let f prime be a function from a to the k minus 1 to f, defined as simple as the left hand side. Okay. Right, so we are summing over all xk in a. Now this is function defined on a to the k minus 1 by to f. And now look at this term. This is a function defined on for variables x1 up to xi minus 1 and xi plus 1 up to xk minus 1. So this is a function. This is a function from a to the k minus 2 to f. This is a function from a to f, right? So each of these terms is a slice for f prime. I mean each product of these two is a slice. So f prime is written. So in the above calculation, f prime is written as a sum of this many slices, right? So the slice rank of f prime is at most, right? So that's what's given by this computation. Now I want to have a lower bound. However, no, not however. we're going to use induction hypothesis. Let's look at the f of x1. If f prime of x1, x2, xk minus 1 is non-zero, then if you look at the definition, if it's non-zero, if this is non-zero, that means this is non-zero for some xk, right? f x1, x2, xk is non-zero for some xk in A, so that means x1, x2, xk minus 1s are all equal. So that means f prime is a diagonal. So by induction hypothesis, the slice rank of f prime is equal to the size of x, where f prime of x is non-zero. All right. Now, I know, how do I know? How do I know that the size of this is big? So what is f prime of x1, x comma x comma x? Is sum over our xk in A. It's f of x1 of the xk. No, not x1. x and xk and h of xk. And this term will be 0 if x is different from xk. So the only place it remains is completely x and h of x, right? And I know that this is non-zero for all A, right? Because we assume that for all A, diagonal entry is non-zero. Remember, in the beginning of the proof, we assume that this is the case. So this is non-zero. How about H? H could be 0, but on A prime, H is non-zero. So this is non-zero if X is in A prime. So that means this is slice rank of f prime is at least a size of a prime. All right, and a size of a prime is at least d, and d is at least a minus I k. All right. So therefore, we know that, right, slice rank I1 plus IK minus 1 is at most, no, it's at least A minus IK, right? So this is the upper bound of the slice rank. And this is lower bound for the slice rank. Yes. So that means slice rank is at least size of A. Okay? So that's the theory, that's the proof. So we know that it's at most the size of A. It's at least the size of A. So therefore, they are equal. All right. Now, in the next video, I'm going to show you how we can apply this lemma to various things, including the capset problem again.